Welcome, and here we go with lesson 1.14, connecting infinite limits and vertical asymptotes. So infinite limits will occur, and what we're looking for is when we approach a certain value, our limit turns out to be infinity or negative infinity. So looking at example 1 here, I see two graphs. One is f of x equals 1 over x minus 1, and the other graph, g of x, equals 1 over x minus 1 quantity squared. It says find each limit and confirm the results with the graph above. So for A, the limit of 1 as we approach 1 from the left of f of x is 1 from the left appears to be going to negative infinity. B, 1 from the right, oops, that's bad. 1 from the right appears to be going to infinity. And therefore, as we look at the limit as x approaches 1 from both the left and the right, we have them go in two different directions. Therefore, we must answer that the limit does not exist. D through F talk about the second equation, the quantity squared equation, and I look at 1 from the left on there, and we are headed to infinity, positive infinity. And from the right side, we are also headed up to positive infinity. Therefore, the answer as we head to 1, they're both going the same direction, so we can answer that it's positive infinity. This also could be answered as the limit does not exist, but I prefer the infinity because it gives more information. Down below it says, think about this. What do limits that produce results of infinity or negative infinity say about the function? Well, when I get infinity, negative infinity, what does it say about the functions? Well, what we noticed in the picture is that we are locating vertical asymptotes. So I'm just going to say they represent the locations of vertical asymptotes. Okay. Now, when we flip to the back side of your notes, mine over 2, we come into the definition of a vertical asymptote, and it goes, if the limit as x approaches c from the left equals infinity or negative infinity, or the limit as we approach c from the right equals infinity or negative infinity, then the vertical line, x equals c, is a vertical asymptote. And since it is a definition, we know we can read this as an if and only if. It's a two-way street. If we have a vertical asymptote, we can expect our limits to be going to infinity or negative infinity. If we have a limit going to infinity or negative infinity, we can assume it's a vertical asymptote. Example 2, determine all the equations that represent vertical asymptotes for each of the given functions. So I've got x squared plus 1 over x squared minus 1. And when I look at this, I would think that I might have problems when x approaches 1 and x equals negative 1, because I think in our domain, we will see that it's all reals except that x cannot equal 1 or negative 1. Okay, I just want to take a minute to write this out. Now, I knew that I had domain issues because I did factor on this in my head. I had x minus 1 times an x plus 1. Difference of squares factoring, set them each equal to 0, each of the factors, and I came up with that. Now what I want to do is just investigate it a little bit further to see, does it go to infinity or negative infinity? Because I realize I'm going to have some issues with those two values. So I wrote my first one out that I'm heading to 1. And if I were to put something a little bit larger than 1 in for x squared, because I want to approach 1, I would have x squared plus 1 over something a little bit larger than 1. And let's just say 1 plus. This would cause us to have, I don't know, roughly 2 up on top, and on bottom, 1 just a little bit larger than 1 squared would be just slightly bigger than 1. 1 minus 1 would be some very small positive quantity. And that tells me 2 divided by something really tiny will go to infinity. And that right there tells me I have a vertical asymptote. Then on the bottom, let's see, also on x squared, let's choose a different color. On x squared plus 1, if I took something slightly smaller than 1 and squared it, top and bottom. So what I'm kind of doing here is I'm breaking out a limit into 2 limits. So this limit, we're coming into x from the left, and that other limit, I came into the limit from the right. Now, on this one down here, if I come in from the left side of 1, that is going to give me something very, very small. It's going to be a very small negative value. I wanted to write small, very small negative. And I would still have roughly 2 on top, and 2 divided by something very small negative would give me negative infinity. So I know there is a vertical asymptote at 1, and it looks to me like we're going to be coming from the right side of 1 heading to positive infinity, and from the left side of 1, call this x equals 1. Imagine that this is a dashed asymptote. That's what our function should be doing. So let's check it out and see if that is the case. I have a picture of that, and there it is. Just as we thought should be happening, we're headed to positive infinity on the right side of 1, negative infinity on the left side of 1. We didn't go and investigate this one, but I would have done exactly the same. I would have broke this out into the limit as x approaches negative 1 from the right, and the limit as x approaches negative 1 from the left of our function, and done the same analysis that we did up here where we talk about, is it a very small negative or is it a very small positive? And we would have got our, let's see, from the right side, it would have went to negative infinity, and from the left side of negative 1, it would have been positive infinity. Okay, so vertical asymptote definitely at x equals 1 and negative 1. So let's just write our conclusion down. Vertical asymptote at x equals 1 and x equals negative 1. Fantastic. All right, let's dig a little deeper into B. So for B, let's slide this over. For B, my function looks like it could be factored up on top, and the bottom definitely can be factored. So let's do the factoring. Factoring always gives us a little bit clearer idea of what to expect. So we are going to factor, and that factoring is going to be an x plus 4 and an x minus 2 for the numerator. On the bottom, we will have an x minus 2 and an x plus 2. So domain-wise, we know it's all reals except x cannot equal 2 and x cannot equal -2. If it were to be either of those numbers, we'd have zeros in the denominator, and that would be division by zero error. Now, you noticed and I noticed that we have a like factor on top and bottom. Those two will cancel each other and create a point discontinuity. So let's also notate that we've got a point discontinuity at x equals +2. So that's going to be that hole in the graph. I suspect that we are going to see a vertical asymptote at the other domain at -2. So at x equals -2. Now to verify that, we should do that same limit analysis. So if we analyze the limit as x goes to -2 from the right, and I really just need to evaluate it x plus 4 over x plus 2. If I put in -2, the top is going to be roughly 2. What I'm trying to write there is that this implies, rather than saying equal, because that's a really strong statement, I'm going to say this implies, here's my thought process, that the top is roughly 2, and the bottom, if I put something slightly larger than -2, say -1.999, and I add 2 to it, I'm going to have a very small positive number. Remember how I thought this through? I had -1.999 plus my 2. And that's where I got this very small positive. So just some analysis going on there. And that means that this would be infinity. And there we go. Now we know there is a vertical asymptote. If I wanted to know what's happening on the other side of -2, then I've got to do an analysis of that. The limit as x approaches -2 from the left of x plus 4 over x plus 2 gives me, on the top, if I put -2 plus 4, I'm getting roughly 2 again, right? Really small numerator. And if I put in -2 from the left on the bottom, I'm thinking in my head like -2.00001. You can put anything that gets really close to -2, but from the left side, I can see my top is around 2 still, no change there, but the bottom would be something very small. Oops, there's a plus here. Very small. But this time it's negative, isn't it? And if I take a positive times a negative, I get negative. So I'm going to end up with negative infinity. Or positive divided by negative, negative infinity on that. So we should see from the left side, we're headed down. From the right side of -2, we're heading up. There's our x equals -2 vertical asymptote. Now let's reveal and see if we do indeed have that going on. And yep, we analyzed very, very well. We would show some sort of whole discontinuity. I'm trying to see where that 2 is roughly there, because we knew we had a point discontinuity at x equals 2. They just don't show up when the graphing calculator or Desmos does it. So fun to analyze functions a little bit more deeply, and you can do it with confidence. It's just looking at it from a limit perspective. Okay, number 3, determine the vertical asymptotes for each of the following. Well, you and I both can see that we have a domain of all real numbers except that where x does not equal 1. All reals except x cannot equal 1. Now, that must mean, because it's not canceling with the top, that I have a vertical asymptote at x equals 1. And you could do that limit analysis for it and come up with that. When I look at cotan, well, let's expand the cotan function. Cotan is, okay, tangent is opposite over adjacent. So cotan is adjacent over opposite. Been a while since I've worked with cotan. And that means I'm going to have cosine x over sine x. Is the same thing as cotan x. Well, I definitely don't want my denominator to equal 0. So when does sine equal 0? At 0, at pi, at 2 pi, at 3 pi, at 4 pi, on the pi's, right? So my domain for cotan is all reals where x does not equal, let's say, n pi, and n is an integer value. Because we want to get at pi, 2 pi, 3 pi, 4 pi, okay? And there's the picture on it. All right. Finally, example 4, find each limit to the best of your ability without using a calculator. Try making a table of values allowing x to get closer to 1 on the appropriate side of 1. All right, so it says without using a calculator. I don't know if that's so necessary, but I would say let's use a calculator if we want to, and we'll go from there. Alrighty, I'm going to pause and get my calculator out. Okay, I've got my calculator set. In the y1 equation, I put 1 over x minus 1. They asked us to make a table. They said without calculator, but let's use our calculator. So the first thing I'm going to do is go second window, get to that table set. Mine was already on ask. Yours might be as well, because I want to be able to input my own values. So I'm going to go to second graph or get to the table, and looks like I got some values in there already. So I'm just going to hit delete. Maybe it won't delete them. There we go. Delete and delete the final one. Now, let's create our table. We know we are going to end up with problems. At 1. This one says to come into 1 from the left side. So here's my 1. From the left side, I'm going to think 0.999, 0.99, 0.9, and that's probably good enough. So I'm going to put in my 0.9. I'm going to put in my 0.99. Oops, I did 66. 0.99 and 0.999. What happens if I put in 1? The obvious error. So we get -10, -100, -1000. I guess we got easy numbers because we were dividing by like 0.1, 0.01, things like that. So obviously this is getting, it's getting large very quickly, or negatively large very quickly. And that tells me that we are headed to negative infinity. And I think we could do that same analysis really easily. Like we could have said, we have 1 divided by 0.9999 minus 1, which gives us 1 divided by very small negative. And I know when I divide by something very small, I get something very large, and that's negative infinity. Coming into 1 from the right side will be another table. And let's draw ourselves another table. This time I'm going to choose to put 1 over on the left side. I like to think of a number line when I do these. So 1.001, 1.01, 1.1, and that's enough. So I'm going to put in 1.001, 1.01, 1.1, and we should see our values. We get 1,110. And we can see how this is growing and reaching infinity. So this limit here would be infinity. And we could have analyzed much like we did up above and came up with that. So the limit is D and E. It's headed to infinity at the end there. So that is what what were we on? 114 was all about. And you may do the worksheet that accompanies this. So good luck.